These programs are for everybody, ages 4 to 94, and in all walks of life. And I am Julius Sumner Miller, and physics is my business, a phrase you have heard now some hundreds of times. And what is our business? In this series, a new one, entitled again, Why It Is So, on light, optics, and some brief adventure into modern physics. First, let me identify that modern physics business. Physics dates from antiquity, Archimedes, Euclid, Pythagoras, and others. Regarding modern physics, we include those things which began, let us say, at the turn of the century, as, for example, Röntgen discovering X-rays in 1905, J.J. Thomson discovering the electron, 1897, the Curies, Marie Sklodowska and Pierre, Rutherford, radioactivity, Becquerel on radioactive activity, and such. Things then in our own day. Now coming back to our principal first business, in optics or in light. I would remind you of the several senses we possess: touch, taste, smell, hearing, sight. And I am led to say, in principle, this: the value of a thing that we possess is best measured by the consequence upon us if we were bereft of it. So, if I were to lose my sense of touch, that might be bad. I could be burned on a stove and not know it. If I were to lose my sense of taste, then all things would likely taste alike, but I could survive with that, not with too great discomfort. If I lost my sense of smell, then an apple and an onion would smell alike, perhaps, which would not be too disastrous. If I were to lose my faculty of hearing, Mr. Pearson, this would be bad. I would not hear the gurgle of a brook, or the flight of a bird on the wing, or the wind in the pines, nor could I hear my friends. So that would be very bad. But if I were bereft of my sight, oh, that would be a terrible thing. Of this I shall say no more, but I've given you something to think about. And what do I mean by that? We should thank our blessings for the faculties we possess so abundantly. Now coming to the subject of light. We treat it in several ways. First, a geometrical way. A geometrical way. By that I mean we will consider a source of light as a candle, say. Here it is. Now, why do I choose a candle as a source of light? Because Michael Faraday did much with candles, and I have a fondness for Michael Faraday. You know that, Anderson. Indeed, I urge you, when you are in London, visit his grave in Highgate Cemetery in a prayerful mood. So we consider a source of light, and we say that the energy goes that way. And all the things we discuss will be with lines called rays. We will discuss reflection. That can be handled on the ray diagram argument. We can discuss refraction. The bending, the change in direction of light when it enters a medium of different density. We can talk about the rectilinear propagation. Rectilinear meaning it goes in a straight line. Rectilinear propagation. And we can make arguments for its finite velocity, meaning it does not go instantaneously, which some indeed in earlier years thought to be. Then we can discuss light on a physical argument. Physical. Here we imagine light to be a wave motion, an undulation, as it was first thought, an undulation in the ether, since it was supposed that light needed a medium for propagation, which it turns out is not so. It goes best where there ain't nothing. The English may not be purist, but you know my method. So we consider advancing waves. What have I drawn here? You know, when you drop a pebble on a quiet pond, you see those ever-growing circles of disturbance, about which I'll talk later. They are the result of some such mechanism. Then we have, finally, the quantum argument, where we imagine light to be made up of little bundles of energy propagated in the stuff in question. The energy of each little quantum being given by some stuff like that, h nu. Well, if you're not used to the Greek, I'll write it hf, where h has a strange complexion. It is Planck's constant, and f is the frequency, which in the vernacular might be called the color. So our first concern is with the treatment of light phenomena geometrically. And my first experiment would be as follows. Supposing I had a cardboard, such as I have here, with a tiny hole in it. Tiny hole. I'm going to make a tiny hole. And supposing I put an object out here, which is a luminous source. Notice I said luminous. We see all things either because they are self-luminous and emit their own light, or we see them by reflection. Those are the two mechanisms, and there are no others. Now, supposing I had a screen here, a white cardboard, what would I see here? I would see as follows. The light from the tip of the candle goes through that tiny hole, and there's the tip of the candle. And the light from down here goes up there. So to make it as clear as I can, I'd see the image inverted. What does this suggest? The hole is a tiny, tiny hole. Light from here went straight. Here's the way we would do it. Come up here, Mr. Anderson. Give me a hand, will you? Here, you will hold the screen. Let's take that lamp behind. I'm going to turn on this lamp, an incandescent lamp with an obvious filament. Right? And there it is. May be bright for the camera. Now, where is my card with the hole? How did we wait a minute. Hold this, Bruce. Yes, I need that. Commentary. We are going to have a very difficult time doing these experiments. Why? Because it is in optics, and optics is very difficult. Hold that right. I'll light this again. And now I'll obscure this from the camera. And now, let us see. Where do we go? It's that camera, right? Oh, we need the lights out, I think. We need the lights out. We need the lights out.
Now we can see it here.
Have you got it? Does it show on the monitor?
Yes.
Does it show?
It's there now, yes.
Yes, there it is. And you see the image is inverted. Thank you, Ray. The image is inverted. So we have established the fact that light travels in straight lines. What's our time? 9 minutes. Mamma mia. Mamma mia. I'm led to an aside. You know what an aside is in drama, an aside or an apart. When I was a little boy reading the comics, I remember seeing Mutt and Jeff. There's one of them, I don't know which one. Mutt and Jeff looking at something here, supposing they're looking at something. And there were little dots drawn by the artist, suggesting that this figure here was focusing sharply on that. And do you know, I think I was about 7. I thought then that stuff came off of that to his eye and excited the sensation of vision. Well, by golly, I was not far wrong, because that's really what happens in the quantum argument. And it is appropriate to abandon our engagement here. We will see you another time. I am back again, Julius Sumner Miller. Physics is our business, and this is our second program in this series on light, optics, and later on modern physics. We have established some historical things, especially the rectilinear propagation of light. It goes in straight lines. Now, would you believe it? I have to say that what I said is not altogether true. That is, I have not told you anything untrue, but I have not told you either all the truth. Light bends around corners, as we shall see later in the subject of diffraction. But our next engagement is with this, the inverse square law. Very important. Supposing we have a source of light, and I put up a card at right angles to it, say a square card. There it is, quite like this, light here, square card. You can see that the light energy emitted by the source is intercepted by that card. So the light energy density, the intensity of illumination, oh, this language gets formidable. Luminous flux, radiation, luminance. Oh, frightful. I'll just forget all the technicalities. The light energy falls on that area A. Let the distance to that area be little d, the distance. Now, let me go another distance d. See, I've doubled the distance. What area intercepts the light energy from the source? Answer, and my drawing will be very crude perhaps. There it is. That's roughly it. And do you see that this area is 4 times the first one? If you remember a little Euclidean geometry, you see this is a rectangular pyramid with a square base, and the areas are to each other as the squares of the altitudes. I'm reciting something of Euclid. Beautiful, you should read it. So, the intensity of illumination here is so much. That same luminous energy is spread out over 4 times the area. So, if you double the distance, you quarter the luminous energy on the surface in question. That is to say that the intensity of illumination is governed by the candle power of the source and is inversely as the square of the distance from the surface engaged. Now, I can prove that, and that's very important, as I tell my students, for example, who do not do their studying as I would expect. If the light, the lamp illuminating the page of the physics book, is at a distance of 1 foot from the page, so much light energy is found on the printed page. Now, if they put it at 2 feet, the light energy is 1/4 as much. If they put it at 3 feet, the light energy is 1/9 as much. I am led to believe that some of them put it at 100 feet because they give their studying so little attention. Now I'm going to show you the inverse square law in a beautiful way, the like of which you could do at home. But I must remind you, for the young people, you use candles and matches and such only in company with your teacher or elders. Here it is. Supposing I have a block of paraffin. I have one here. In fact, I have 2. I'm going to have 2 blocks of paraffin side by side, and I'm going to put a little sheet of aluminium foil between. You see how I've learned, Mr. Anderson, to accommodate to the environs. Oh, have to take a moment out. You know my philosophy from other days. Here I am taking a drink of water. I am led to contemplate it, I think, more than others generally. Be mindful of this. It is 2 gases locked together by some affairs of nature, H2O, in a manner necessary for my chemistry and well-being. I tell you, Bromhead, that's something to contemplate. But who does contemplate it? Hardly anybody. They drink the water and never give it any attention, Anderson, which is pathetic, isn't it? Yeah. I'm reminded, too, of Newton. What did Newton say about things? It goes something like this. Everything is designed in such a fashion as to suit the purpose for which it is intended. That's beautiful, beautiful. But anyway, this is my paraffin photometer. See, photometer, photometer, photometer. I have these two blocks, and I am going to put one candle here, one candle, and it is so far from that first block. Clearly, that first block will be illuminated. That is, it'll show by reflection such intensity of illumination. Now, I want the other one to be equally illuminated. If it was of the same candle power, I'd put it at the same distance. But supposing I have two candles, as I will show you in a moment, isn't it clear that these two candles should be nearer? No, you see, I am doing it like a beginning student. Could not the two candles be farther, Mr. Bromhead? Hey, to give the same illumination. And indeed, that is so. So, if now I light the candles, you will see, mark you, first, if viewed this way, I got it all right? Yes, they are equally illuminated. Now I'm going to light this candle. Now, this one shows a little darker, clearly. If we could have the lights out. Can we have the lights out? That's it. Oh, look how dark that one is. Look it. Now I'm going to light these two. They are equally illuminated. Now, I'm going to regulate that a little bit. That's about it. Now, let's have the lights, and I will show you. Notice I don't want my candles to burn down unequally. I'm going to show you that if this is the first, and this is the first distance, and this is that, and this is the second distance, the intensity of illumination on here is C1 over D1 squared, and the intensity of illumination there is C2 over D2 squared. Now the intensities of illumination are equal, and therefore C1 over D1 squared is equal to C2 over D2 squared. But don't I have twice the candle power here? So I'm going to put 2 C1 there. And now if I made a measurement of the distances, from the source here to the opaque aluminium there, I would find it roughly 5 inches. And this one, I would find roughly 7 inches. And if you put the mathematics in there, Mr. Anderson, it may come out quite right. I'm led to say as Isaac Newton did, I extended gravity to ye orb of the moon and found it answer pretty nearly. Now when we do this for real, we find it answers only pretty nearly. And the reason is this. I do not have 2 identical candles here, that is 2 like that. They are 2 separate ones. And therefore they constitute 2 sources, not 1. And therefore the mathematics does not come out quite right. Which leads me to conjecture on the following. Supposing you had a choice of having 2 25-watt lamps in a certain fixture at home, or 1 50-watt lamp, would you not think that 2 25s would give you the same as 1 50? It turns out not to be so. The 150 gives you more. The 1 50-watt lamp gives you more. The single, notice when I say 150, it sounds like 150. The 1 single 50-watt lamp gives you more than twice the 2 25-watt lamps. And the mathematics of that leads us astray, which suggests what? If you're going to buy some incandescent lamps, buy 150, it may cost less than 2 25s, which is a good note on which to end. And I'll see you another time. How do you do, ladies and gentlemen, and boys and girls? I come again as Julius Sumner Miller, and physics is our business, and this is optics. And you remember the last program ended on the paraffin photometer, and I was about to make a measurement. Indeed, I did, but I didn't realize how well it was coming out, or how good. I measured this distance and found it to be about 5 inches, and I measured that distance and found it to be about 7, and I dismissed it. But then, when we ended the show, I explored it further. Here's the one candle at 5 squared distance, that's 25. Here are the 2 candles at 7 squared distance, which is 49, and you see that 2 times 25 is pretty nearly 1 times 49. And that's about as best as I've ever had it come out. Now, why has it not come out good in other times? Answer: always some stray light around, which disaffects our operations. So, you see, experiments don't fail. Remember my philosophy on that. An experiment does not fail. If we want nature, which you always spell with a capital N, to do what we want it to do, then we must provide for her conditions precisely. Now, we have a model of that inverse square law, which I should show you. Here is a source of light. I'll look at the monitor to see how best. That's all right. Here is a source of light. Its energy is intercepted by this area A at a distance d. At a distance twice as far, its energy is spread out over 4a, and at a distance 3 times, its energy is spread out over an area 9a. The inverse square law, Mr. Anderson. Thank you. Now, let us rub out this board and go to a new matter. Why is it this board gets rubbed out? Answer: friction. And you remember in an early program in mechanics, friction is mu times a normal force, where mu is the coefficient of friction and n the push at right angles. It is clear that if I don't push so hard, n is very easy and the force of friction is very feeble. But if I push, you see, it rubs it out very well. Things should be done with force and firmness, Mr. Bromhead. Now, the laws of reflection. Reflection. Supposing I had a reflecting surface. Here is a mirror, a tabletop, a barn door. That doesn't make so good a mirror, but it's still a reflecting surface. If it wasn't, you couldn't see it. Supposing I have a source of light here, and by the ray argument, I draw one ray. We will call that the incident ray, cap I. Now I'm going to draw a perpendicular to that surface, and that line in the blackboard there makes it easy. That perpendicular to the surface we call the normal to the surface. Normal does not mean ordinary or commonplace. It means perpendicular in our language. Now, what happens here? What happens here depends upon the nature of this stuff. This is air. Let that slab be a thin slab of glass. So there is some reflection. How do I know? I'm going to explore the region in here. I'm going to put my eye at various places. I could do that with a with a little tube. Oh, yes, I find this place where I get the mostest light. The mostest light. The mostest. That's the superlative of most. That is the reflected ray. Here is my eye. Right. We will imagine further that I have hidden the source from me so I don't see it. Now, what will I find? A wonderful thing emerges. That angle there, we call the angle of incidence, I-N-C-I-D-E-N-C-E, and this angle we call the angle of reflection, which I label little r, and I is equal to r. Marvelous. And it holds for all kinds of surfaces. Plane surfaces, curved surfaces, refractive, all kinds of surfaces. Further than that, we find that the incident ray, the reflected ray, and the normal to the surface lie in one plane as I have them in the blackboard. Let me illustrate. Supposing this is the reflective surface. Here is the incident ray. Here is the reflected ray. Here is the normal to the surface. Now, this reflected ray never goes off that away or that away, always in that same plane. Very important for our later exploration. Now, let us consider it another way. No, don't want that. I'm going to have a mirror. A plain mirror, the glass very thin, very thin. We'll see the consequences of having it thick. Glass very thin. Let me put my source right here. Source. Let me put my eye right here. Let me put a barrier between the source and my eye so I do not see it. What do I see in the mirror? Answer, an image of the source. Where is the image? Behind here. How far behind? And what does it look like? Answer, let me draw a ray, any ray of light, making an angle of incidence I. It passes upon reflection. See, I had my eye in the wrong place. I'll just move my eye. It passes upon reflection to my eye. Remember, that angle is equal to that angle. Remember, I don't see the source, but I see the image back here. And when we do the mathematics, which I'll not do, and do the geometry, which I need not do any further, I find that that distance is equal to that distance. So the image is as far behind the mirror as the object is in front. Now, any other ray that I would draw would come upon reflection to the eye and fall at the image distance. So every point of the source is in object space, is imaged in image space. Now I'm going to do it for real with a mirror and ask some questions about the image. Here is a mirror. Here is an object. Here is the object distance. I'm going to label it P. We have already established the fact that the image is right here, I, and we'll label the image distance Q. Now I'm going to show you the mathematics that identifies the image. We can show mathematically that 1 over the object distance plus 1 over the image distance is 1 over the focal length. Now the focal length. Oh, what is the focal length of a plane mirror? Here is a plane mirror. You can see that this has an infinite radius of curvature, because if I were to draw a curved mirror and a bigger curved mirror and a bigger curved mirror, pretty soon I have one which is a plane mirror, John. And the radius would be infinitely great. So the focal length of a plane mirror is infinite. If that is so, 1 over P plus 1 over Q equals 1 over that. Now, we don't make that mathematical operation, but it leads at once to making this 0, and therefore 1 over P is equal to minus 1 over Q, and therefore Q is equal to minus P. What does that say? It says that the image distance is equal to the object distance, but you see a minus sign. We ascribe to the object distances a plus sign and to the image distances a minus sign. And see how nicely, Mr. Bromhead, it all comes out. The image distance is the negative of the object distance. Now, you look in a plane mirror. You have all looked in the plane mirror thousands of times, and I want to ask, how do you characterize the image? We have to answer the following questions. First, where is it? Second, is it real or virtual? Third, is it inverted or erect? 4, what is its magnification? And to these matters I address myself in the next show. Thank you for listening.